Now we're getting into another interesting area, and that is the suspension of organic material in calcite. And this is so important to the Microscopy Society of America that they actually had a section in one of the annual meetings where they called for papers on cells suspended in calcite. So they're very interested in this. So this is an area we really want to look at. So here you've got a Haversian system. That's a clot. Look at this clot. There's a canal going this way. That's all clotted. Now, iron, when it gets oxidized, it comes out of the red blood cell as heme. You've heard of hemoglobin. And so that iron further degrades and is oxidized. And it combines with oxygen, sulfur, and other minerals. And so when it does so, it forms rhomboids. Rhomboids, technical term, but they're basically just spheres. You can imagine something with like a pearl, right? They put a seed in, right? They use a seed to start that pearl. And you can actually, when you thin section these rhomboids, you can see that seed in UV, and you're going to see that in a second.
Question for you, Mark.
Yes?
Why are the vessels going at right angles to each other? Wouldn't they all be going in the same direction?
No, they crisscross each other. There are canals called Volksman Canals that will go between two Haversians. You can see that on the bone diagram that I showed at the beginning. I can show that again. But now, canals can go any which way. So, yeah, it's a good question. But look at these cells now. These are completely suspended in mineral. This is hard rock, crystalline calcite. You can almost make out, red blood cells. They're kind of squished at the center, right? If you cross section them, or and look at them on the side, it's shaped like a figure 8. It's squeezed in the center, and so you can almost make that out here on some of these. But I don't think these are RBCs. I think these are rhomboids because a lot of these organisms have nucleated red blood cells, and we're not finding nuclei in these. But again, this is dimetrodon. So, all right, what do the clots mean? We talked about disseminated intravascular coagulation, shows death by drowning. If you fall over on the ground and die, your blood pools. It pools to the lowest part of your body. Okay? This is forensics. This is all in the forensics literature. And so to find clots throughout the organism means that they didn't fall over and die, which is the paradigm that's often taught to our children. Oh, these creatures were just walking along and they fell over and died, and somehow they got a little bit buried. And no, we think these were killed by drowning. The clots sequester the iron from Fenton reactions. This is the big explanation for how these vessels are preserved. There are 2 papers in the literature that described the action of iron on soft tissue via Fenton reactions to preserve the tissue. It goes like this. Native naked iron is oxidized when water flows over it, and it forms hydroxyl and peroxyl highly oxidative molecules. And these things go around and chew up tissue like crazy. They're highly destructive in living systems. Fenton reactions can kill you if you're not careful, because if you have, and there is a condition where you have too much blood in your iron, and sometimes that can cause Fenton reactions, and you start to eat your own tissue. So Fenton reactions are very dangerous. But the story goes that somehow in vessels, there are collagen fibers that are support structure in the vessel, and somehow these peroxyls and hydroxyls come in and they denature the protein. They twist the protein around into a knot. Okay, and that somehow stabilizes the vessel through time. Now, the Fenton reactions are not going to stabilize every single peptide in that protein. So there's still bonds that are free and open to hydrolysis or autolysis or all of these normal cellular functions that happen when tissue degrades and dies. And so it's an insufficient explanation because it doesn't provide enough bonding. Now we use, when we put soft tissue under the microscope, we preserve it in an aldehyde first. There's a chemical called formaldehyde, you've heard. Okay, we dilute that, we call it formalin, and we put our tissues in there to stabilize them. And what are they doing? They're cross-linking every single bond in the protein. So when I take tissue and I preserve it in an aldehyde, and then I dehydrate it, take the water out of it in thin section, I'm going to see beautiful structure, particularly if I do it all on ice. If I process my tissues in ice, which is how I was trained as a soft tissue expert, do it on ice, then your structure remains. You can thin section it and examine that at very high magnification under the microscope. Fenton reactions would not preserve the structure that we're seeing. It would actually modify the structure. And because we were able to compare chicken nerves, which I pulled out of a chicken nerve, a chicken bone, to the nerves that we were finding in Triceratops condyle, the bone at the base of the skull, we made an exact match because the structure matched. So morphology is really, really important. And Fenton reactions are not going to preserve your morphology. They'll change your morphology. So you may not know what you're looking at. So we think Fenton reactions are really not a great explanation for preservation. I don't know why they're preserved. Okay? As a tissue processing expert, that's what I did for 12 years in academia. I cannot tell you why these tissues are still preserved with the structure intact. I have no clue. So the clots would sequester those Fenton reactions in the canals. So they would not be able to get out to the tissues and preserve them. Clots limit the water flow. You must have water flowing through your bone to get Fenton reactions. Doesn't happen otherwise. So they inhibit water flow. The iron experiment that I discussed, they did two of them. The first one, they actually used blood, but they highly purified it. The first thing they did to the blood that they were using for the experiment is that they put an anticoagulant in it. Now think about that, folks. Was the dimetrodon blood put in, had an anticoagulant put into it to prevent it from clotting? No. These things did clot. Blood clots. It knows when you get a puncture wound. And it starts the cascade. It's an automatic thing. You don't have to think about it. You don't have to tell your blood to clot. It does it automatically. And so they had to prevent that. Why? They couldn't get to the heme. They couldn't expose the heme for their iron preservation if the blood was clotted. So the first thing they did was add anticoagulant. Then they started high-speed centrifuging them. And I'm talking 30, 40, 60,000 RPM or faster. And so they removed all the cell membranes. Why? Cell membranes initiating the clotting cascade. Okay? There are tissue factors in there that cause the clotting cascade to begin. They had to remove those. All the platelets, those little cells that assist in clotting, had to remove them all. They did 6 times through high-speed centrifuge. And then they used molecular filters. They were filtering out molecules from the blood in order to get the blood to preserve the tissue. So, and then what they did is they just soaked the blood vessels for 2 years in that concoction on a air-conditioned laboratory bench, and they said, voila, we've explained Hell Creek. No, I don't think they have. I think it was a desperate move. I don't think it's good science. Frankly, I think it's embarrassing. And I think our answer is a better answer, that these guys actually died by drowning.
Hey, Mark?
Yes?
Now, even if that were the case, even if what Schweitzer did was true, that doesn't explain, I mean, you'd have to multiply by 1,000,000 in order to get what the time period. It might more likely explain why it would last 4,000 years, right?
Possibly, but, again, the blood is all still in the canals, so it's a moot point. But, no, again, the discussion of preservation. What is preserving these things? I don't know. So yeah, no, it's an inadequate response. One of the things I suggested is Dr. Schweitzer go patent it right away, Because if it is preserving tissue for 68 million years, there are some very rich people who'd like to have their bodies preserved. So, you know, you can soak them in dinosaur blood or something. I don't know. Okay.